Hi again. So the objectives this time will be to use electron configuration to understand electronegativity and first ionization energy, and we will illustrate the meaning of atomic radius. To start, the definition for electronegativity is the affinity of an atom, the affinity the atom has for acquiring new electrons. So in other words, it's a pulling force for stealing electrons from other sources. On the next slide, we'll take a look at electron configurations to see what that really means. So here we have our periodic table. We're going to take two examples of electron configurations and examine them a little bit more closely. We'll take a metal, which is on the far left. Let's go for maybe sodium right here, and a nonmetal on the far right. And let's grab fluorine. Let's take a closer look. And the electron configuration for sodium is 2-8-1, while fluorine is, where is it? There it is. It's 2-7. So we're going to take a closer look at those. And let's write sodium. Sodium was 2-8-1. And let's put down here fluorine, which was 2-7. All right. First, let's inspect sodium. The octet rule says that the outermost shell of any atom wants to be complete. So in order for sodium to achieve this, it could do two things. It could acquire 7 electrons, or it could lose the 1. Now the simplest thing is losing 1, giving it a brand new electron configuration of 2-8. Sodium would also then take on a positive charge, positive 1, because there are more protons than electrons. But the real story here is this. Sodium does not want its outermost electron. So according to electronegativity and affinity for electrons, it has a very low one. It wants to get rid of its outermost electron. So it has a low electronegativity. Now let's look at fluorine. Fluorine is 2-7. To stabilize this atom, to satisfy the octet rule, two options: lose 7 or gain 1. The simplest thing would be to gain 1 and acquire an electron configuration of 2-8. So fluorine really wants to gain an electron. It has a high electronegativity. In fact, fluorine has the highest electronegativity at 4.0. Now, first ionization energy is defined as the amount of energy needed to forcefully remove an atom's outermost electron. So it's going to be one of those valence electrons. Let's look at some electron configurations to explore what that really means. So for this one, let's examine sodium and potassium, and then perhaps even fluorine and chlorine. Let me write them here. Sodium from the last slide was 2-8-1. Potassium, which is just beneath it, must be 2-8-8-1. I'll also put down here in the lower right, fluorine was 2-7, while chlorine then must be 2-8-7. All right, let's get this out of our way. Now remember, first ionization energy says, how much energy would it take to remove the outermost electron? Let's first compare sodium versus potassium. How much energy would it take to remove this outermost electron versus this one? And what you need to consider is this. Here would be a nucleus, and here would be a nucleus. Yes, these 1 electrons are not wanted by these atoms so that it could satisfy the octet rule. But which one of these would allow the electron to leave easier? Well, the protons in the nucleus of this sodium have the ability to pull on this 1 electron more forcefully than this potassium could pull on this electron, just because it is closer. So let me grab a pen here. So the first ionization energy for sodium would be higher than that for potassium. Again, that is because of the position of the last electron versus the nucleus. Now let's examine fluorine versus chlorine. Well, would it be easy to remove those electrons when in fact fluorine really wants them? Not only does fluorine want other electrons, it will definitely want to keep its own. Chlorine wants other atoms' electrons, so it will definitely keep its own. But I'm curious, which one would require even more energy to remove? Again, let's consider the idea that I mentioned just above, the nucleus. The outermost electrons for fluorine are so much closer to the nucleus that positive charge from the nucleus will pull those electrons in quite strongly when compared to that for chlorine. So the first ionization energy for fluorine would be higher than that for chlorine. Moving on to atomic radius. Atomic radius is defined as half the distance between two nuclei of bonded atoms of the same element. Now I know classic definition of a radius would be, if that's a circle, definition of a radius would be from the center to the outermost margin. Okay, but for some reason, to get an accurate measurement, you actually have to have, let's put another circle there. We have to have two atoms bonded together in order to achieve this. And what that would then look like is, well, from this nucleus here to this nucleus here, well, and then we have to take half of that amount. Let me change the pen. So we would go from here to right here, which is half the distance between the nucleus of one atom and the nucleus of another. And last, I just want to show you table S, because on table S it will give you these values. Here are the atomic numbers for the elements with their symbol and name. Here we have the values for first ionization energy as kilojoules per mole. Electronegativity, now that does not have a unit, it's an arbitrary value, and fluorine having the 4.0 is the highest, so everything is kind of measured against fluorine, and here we have atomic radius measured in picometers. So just to recap, we talked about electronegativity, which relates to the affinity an atom has to acquire new electrons. First ionization energy, which relates to the amount of energy it takes to have an electron removed from an atom. And atomic radius kind of relates to the size of the atom itself.